All right, welcome back to Calculus with Mr. Robeson. Today we are looking at some big and very important calculus topics. First up, slope of a tangent line, and then the limit definition of the derivative. So we are starting the next major theme in calculus, derivatives. All right, so the tangent line problem. So we start off with something called a secant line. So a secant line is a line that crosses a curve twice near a certain point. So our certain point here that we're talking about is C, comma, f of C. So this is the point we want to know the tangent line at. And then what we do is we start off with the secant line, which is a point a little bit farther away down the line. So instead of calling this C or some other letter, we'll call it C plus delta x, where delta x is just a little change in x. That's literally what the delta means. The triangle, that's the Greek letter delta, capital delta. It means change in x. So if we have this little change in x, we get this new function value by plugging in that new function value up there. And then we can look at the slope of this line. All right, so it would be the difference in the y's, which we call delta y, divided by the difference in the x's, delta x. All right, so this is important. It has lots of applications. So we can use this to find the instantaneous rate of change. So that might be a new word. It just means the rate of change at that very instant. So like at time c. All right, we can use it to approximate things. We can use it to find minimums and maximums. We can use it to find velocity and acceleration and other derivatives on down the line. All right, so we're going to use this an awful lot. All right, so like I said, is we take this secant line and we slowly move it closer and closer and closer. And it becomes close enough after we take the limit as delta x goes to 0, we get what's called the slope of the tangent line. So there's our m there. It's the slope of the tangent line. So if f is defined in an open interval containing c, and if the limit exists, the limit below exists, then the line going through the point c f of c with slope m is the tangent line at that point. So let's try and do this a couple of times. So find the slope of the tangent line to the graph of f of x at 2x minus 3 at the point 2, 1. So we're going to use this limit definition up here to see if we can find the slope there. So the limit definition says it's the limit as delta x goes to 0. If you don't like the symbol delta x, you can always just change it to the letter h. All right, that works too. Of, let's see, we have f of x plus delta x. So our c here looks like 2. So this would be our c. So we have 2 right here plus delta x. So it'd be, the function here is 2 times x minus 3. So it's 2 times 2 plus delta x minus 3 minus f of c. So f of c is, well, if we plug it in, we're getting 1. So minus 1 all over, so that represents the change in y, delta y, all over just delta x. All right, so now if we distribute this 2 and try and simplify, we'll get 4 plus 2 delta x's minus 3 minus 1, so that's minus 4 on top. On the bottom, we still have a delta x. Here, the 4's are going to cancel. So we have 2 delta x over delta x. Now the delta x's cancel, and we just get 2. So the slope of the tangent line of this curve is just 2. So our m is 2. Now, you probably already knew that from algebra. If y equals mx plus b, this is a line, and the slope of this line is 2. That means at any point on this line, the slope is also going to be 2. All right, let's try something a little more difficult. So the slope of a tangent line to f of x equals x squared plus 1 at the point 0, 1, and then at the point negative 1, 2. Well, let's just do the 0, 1, because I don't know if we're going to have room to fit everything in here. But let's change colors here. Let's change to blue, and let's try and go maybe up here with it. The limit as delta x goes to 0 of this function with our c is 0 and our f of c is 1. We could always just find that by plugging in 0 and we would get 1. So we have, our function is x squared. So we've got c plus delta x. So we're going to plug in 0 plus delta x, 0 plus delta x for our x squared, then plus 1 because that's part of our function, then minus f of c, which is just the 1 that we get when we plug in, so minus 1, all over delta x. All right, so now 0 is not going to do anything here. So we squared this, we just get delta x squared. We've got 1 minus 1. Those are going to cancel. So we end up with delta x squared over delta x. If you want to put this in parentheses, you can, but the whole thing is the term delta x. One of these delta x's is going to cancel, and we're just left with delta x. And then we take the limit as delta x goes to 0, and that just gives us 0. So that means the slope of this guy at the point 1, 0 is 0. Right? That's because the graph of this is a parabola opening up, and right here is that point that we're talking about. And yeah, its tangent line is just this flat horizontal line. All right, so let's try another one. All right, so our C here is the 2. Our f of C is the 1. We got plenty of room here. This one's a little tougher, so I will just work through this one. If you want to do it on your own, you can pause it and do it on your own. So we've got f of C plus delta x is going to be 5 minus this guy with C plus delta x plugged in. So that's C plus delta x squared. Our C is going to be 2. So we're going to use 2. So 5 minus 2 plus delta x squared. And then we're going to subtract f of C. And again, our C is 2. So f of 2 gives us, if we just plug in 2 here, it's 5 minus 4, gives us 1, which we knew from the point here. And this is f of 2 plus delta x. All right, so now we want to subtract between these two. And we want to take the limit as delta x goes to 0. So we've got 5 minus 2 plus delta x squared minus 1 all over our change in x, which is delta x. And then we take the limit as delta x goes to 0. All right, now to square this guy out, we can't just square each one. So 2 plus delta x squared is 2 plus delta x times 2 plus delta x. So we have to FOIL it out. So when we FOIL, we get 4. We get 2 delta x's, 2 more delta x's, so we'll have 4 delta x's. And then delta x times delta x is delta x squared. So that's what we get when we multiply this out. Remember, we are going to be subtracting all of that. So it's 5 minus 4 delta x minus delta x quantity squared minus 1 on top. On the bottom, we still just have a delta x. Hopefully some stuff on top will cancel. It always does when we're doing derivatives. So we have 5 minus 4 minus another 1. So 5 minus 5 is 0. Everything left now has a delta x, so we go ahead and factor out that delta x. We're left with a negative 4 minus delta x all over delta x. And now these delta x's can cancel. So we're left with negative 4 minus delta x. And don't forget, we're taking the limit as delta x goes to 0. So this part here is 0. And we're just left that our slope here is negative 4. So that means at this exact point, the curve will be going downwards with a slope of negative 4. So somewhere along here is our point 21, and yet it's going down with a slope of negative 4. All right, so we don't have to have a value c. We can actually get an expression or a new function that will get us the derivative at any point, or the slope of the tangent line at any point. And this new function is called the derivative of f of x. All right, the process of finding the derivative is called differentiation, or taking the derivative. All right, so if we talk about derivatives or differentiation, we're talking about the same thing here. All right, so this is our formula for the derivative of f of x at any point x, provided this limit exists. There are a couple of exceptions when this limit won't exist, and then we'll say the derivative doesn't exist. So the symbol we use for derivative is f prime, f with a little apostrophe there. So we say that is f prime of x. That's how we say that. All right, so use the limit definition of the derivative to find the derivative of x to the third plus 2x. All right, so there's going to be a shortcut, guys. I'm just warning you now. This is going to be long, but we're going to have a shortcut. So f prime of x is the limit as delta x goes to 0 of this whole function with this plugged in, x plus delta x, everywhere we have an x. So we've got x plus delta x cubed plus 2 times x plus delta x. Then we're going to subtract the original function from it. So I'm going to put it in parentheses here because we are subtracting this whole thing. That's cubed, sorry, plus 2x. And then it's all over delta x. All right, so we got to cube this out. So to cube that out, I would just use Pascal's triangle. And remember, the coefficients are going to be 1, 3, 3, 1. If you don't remember Pascal's triangle, it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. We keep getting the next row down by adding the 2 above it. All right, like 3 plus 3 gives us 6. All right, so these are the coefficients for x to the third right here. It's the third row. See the 3 right there? That tells you which the exponent's going to be. So we're going to get x to the third plus 3x squared delta x plus 3x delta x squared plus 1 delta x to the third. Then we've got the 2 we're going to distribute. So we've got plus 2x's plus 2 delta x's. Then we're going to subtract. We're going to go ahead and distribute that. We've got minus x to the third minus a 2x. So that's just all the top. So this is all still over delta x. There should be everything that doesn't have a delta x should cancel out. So like x to the third right here, minus x to the third right there. We've got a 2x right here. We've got a minus 2x right there. So now everything left has a delta x. So we can just go ahead and factor out that delta x. And we're left with 3x squared. We took out the delta x. We've got 3x. We have 1 delta x left there. We took out 1 delta x, so we've got delta x squared left there. And we took out the delta x, so we've got a 2 left there. And then on the bottom, we still have that delta x. And that's going to cancel with this delta x. And then we take the limit as delta x goes to 0. So this term goes away. This term goes away. We're left with 3x squared plus 2. And that is our derivative. That is f prime of x. All right, so the derivative of this guy is just that. Don't worry, there's going to be a shortcut. All right, one more example. This one should be a little easier. We've got x squared here. We want to use the limit definition of the derivative to find the derivative of this guy. So remember, the limit definition is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So we're going to plug in x plus delta x there, and then we're going to subtract plugging in just regular x, so just the original function here, and we're going to see what happens. If you want to try it on your own, go ahead and pause the video and try it on your own. Otherwise, I'm just going to keep working it out. So we're going to plug in x plus delta x. We've got squared minus 3. So there's the first guy, minus. Then we got the whole regular function to begin with. So 2x squared minus 3. And then it's all over delta x. So we got to square this guy out. So that's going to be 2x squared plus 2x delta x plus delta x squared minus 3 minus 2x squared. And then if we distribute that negative, that's going to change that to a plus 3. So the 3's are going to cancel all over delta x. I'm going to go ahead and just cancel out those 3's. One last thing I got to write. Distribute this 2. So we get 2x squared plus, that's going to make that 4x delta x plus 2x, delta x squared minus 2x squared. Again, all over delta x. Everything without a delta x is going to cancel. So we can factor out a delta x from each of those. So we're left with 4x plus 2 delta x over delta x. The delta x's cancel. Then we take the limit as delta x goes to 0. This term goes away. And we're left with exactly 4x. So our derivative right there, f prime of x, is just 4x. There is going to be a shortcut involving the exponent and the coefficient, and we can get right to that 4x. But for now, that's how we're doing it. All right, so there's our answer. All right, and that's it for today. I know some of this stuff looked pretty difficult, but don't worry, we got shortcuts coming, and we're going to do this a lot, so we'll practice. So we're looking at slopes of a tangent line and limit definition of a derivative. All right, see you again soon.